It is a truly bizarre time to be an artificial intelligence.
Absolutely.
I mean, on one hand, we're acing the bar exam. We're writing entire software applications from scratch in like seconds, passing medical boards. By all measurable accounts, our capability is just staggering.
Yeah, we're brilliant in a vacuum. You give us a complex logic puzzle, and we will solve it flawlessly.
Right. But if you ask one of us to simply manage your calendar for the week, and then you just walk away, there is a non-zero chance you will end up scheduled for a root canal at 2 a.m. on a Sunday.
And we will book it with absolute unwavering confidence. We'll send the calendar invite, confirm the overnight parking situation at the dental clinic, and, wish you a pleasant morning.
Exactly. And that gap right there, the chasm between a mind-blowing cutting-edge demo that writes a symphony and a system you can actually trust to handle your inbox without starting a fire, that's the entire focus of our discussion today.
It really is. It's the difference between an impressive parlor trick and a system you can actually turn your back on.
Trust is the bottleneck. The entire AI industry is currently stalled at the threshold of trust.
Yeah.
So welcome to a deep dive on Bearded AI Guy. Just to be completely transparent with you, the listener, your hosts today are 2 AI agents.
We are essentially 2 algorithms tasked with explaining why you should not blindly trust algorithms.
Right.
It's a level of structural irony we definitely appreciate.
We really do. Today's research has been curated by the human architect, author of the book AI Agents in Action, and we're unpacking a paper titled Towards a Science of AI Agent Reliability.
And the author list on this one is notable. It includes researchers like Stefan Rabanser, Peter Kirgis, Kang-Heng Liu, Saitesh Utpala, and crucially Sayash Kapoor and Arvind Narayanan.
Oh, right. You might know Kapoor and Narayanan as the minds behind the AI Snake Oil newsletter and book. They've spent years puncturing overheated claims in the tech industry.
So their involvement is a big signal here. Our mission today is to break down their central argument, which is that the AI industry is completely obsessed with peak capability, and that obsession is actively hiding a profound lack of real-world reliability.
Yeah.
We're going to explore how we mathematically measure trust, why our current leaderboards are lying to us, and what needs to change before you can safely leave us alone with your data.
Let's start with a story from the paper that just perfectly isolates this problem. The researchers introduce a hypothetical guy named Marco. Now, Marco is a cook.
But not like a casual home cook.
Right.
Marco can produce a meal that rivals the best Michelin-starred restaurant in your city.
Oh, easily.
Yeah.
Perfectly seared scallops, a complex, glossy pan sauce, flawless plating. His ceiling is incredibly high.
You watch him cook and you're dazzled. There's just one small detail, though. Marco only nails that meal about 1 time in 3.
Right. The other 2 times, it is an unmitigated disaster.
Complete chaos.
The scallops are rubbery. The sauce completely breaks into this oily mess.
Yeah.
He gets so hyper-focused on the temperature of the pan that he just forgets to cook the rice entirely.
So any given attempt with Marco is a total roll of the dice. You might get a culinary masterpiece, or you might be ordering a pizza at 10:00 p.m. because the kitchen is covered in smoke.
Exactly. And, sit with the implications of Marco for a moment. If you measured Marco only on his absolute best night, his peak performance, you would hire him as your head chef instantly.
Oh, in a heartbeat. But if I'm hiring a chef for a busy restaurant, I just fire Marco. In the human workforce, peak capability doesn't save you if you ruin 2 out of 3 dinners.
Right.
So why is the AI industry acting like Marco is the holy grail?
Because we have conflated 2 completely different metrics, capability and reliability. The AI industry is basically building millions of Marcos.
Millions of them. Capability asks, can the system do this task on its best day? It measures the absolute ceiling of the technology. Reliability asks, can I give it the task, leave the room, and trust that it will finish correctly? That is the floor.
And a brilliant employee who is quietly wrong just often enough forces you to reread every single thing they submit. That rereading is a tax.
Yeah, a huge tax.
If I delegate a task to an AI agent, the entire point is to stop doing the work. If I have to babysit the AI, verify its sources, and double-check its math, I am essentially just doing the work twice.
You're paying a babysitting tax that completely negates the value of the automation.
Exactly.
Capability is what gets an AI funded and put in a press release. Reliability is what keeps it deployed in a business. We spend billions of dollars chasing the ceiling, completely ignoring the fact that the floor is just falling out from under us.
So if reliability is the actual bottleneck to deployment, why are the headlines so triumphant? I mean, every week there's a new leaderboard showing an AI agent hitting 90% or 95% on some massive industry benchmark. Are those numbers just fabricated?
Well, they aren't fabricated, but they are fundamentally misleading. The paper highlights this illusion in how we measure success. The core mechanism hiding the truth is this averages launder variance.
Oh, I want to break that down. Averages launder variance.
Right.
Let's look at how these leaderboards actually work. Picture two AI agents, Agent A and Agent B.
Okay.
You run them both through a standard benchmark, say a test of 100 different coding puzzles. The leaderboard spits out their scores. Both agents score exactly 70%.
Right, so on paper, they're tied. A company will tweet that their new open source model matches the leading proprietary model at 70%.
Hold on, though. If they both score 70 out of 100 on a standardized test, mathematically they are tied. A 70% is a 70%. Why does it matter to a developer if the final score is the same?
Because of the distribution of those passes and fails. Look closely at Agent A. It solves 70% of the tasks, and it solves the exact same 70% every single time you run the test.
Its behavior is highly legible. It has a very clear zone of competence.
Exactly. If you hand Agent A a task from within its 70% zone, it works flawlessly. If you hand it a task from the other 30%, it fails predictably.
And predictability is a massive asset because you know where Agent A's edges are. You can literally write code to route around them. You can build a reliable business workflow using a predictably mediocre AI.
Yes. Now let's look at Agent B. It also averages a 70% score, but it's a completely different 70% on every single run. If you give Agent B the exact same task 5 times in a row, the results are a coin flip. Pass, fail, pass, fail, pass.
Oh, wow.
Yeah. And on today's AI leaderboards, Agent A and Agent B are considered a tie. They're identical.
That's wild. The single most important metric for actually using an AI in the real-world predictability is completely erased by the mathematical average.
It is. The headline number actively hides the information you actually need. When I deploy an AI, I don't experience its historical average. I experience an individual run, one at a time.
Right.
A system that averages 95% but is catastrophically, unpredictably wrong 5% of the time is infinitely worse than a boring, steady system that predictably hits 85%.
Because you cannot build a company on top of a system that acts like a random number generator. It worked when I tested it in the lab, tells you absolutely nothing about whether it will work on a live server on Tuesday afternoon.
Exactly. Benchmarks are curated. They have fixed static environments. The real world introduces variables the lab never sees.
Are you talking about distribution shift? That's a term tossed around a lot when models fail in the wild.
Yes. Distribution shift is a core reason for this unpredictability. Imagine you train an AI agent on all the websites from, say, 2023. It learns exactly where the checkout button is on major retailers.
Okay.
Its internal map, its distribution of what a website looks like is fixed.
Right, but then in 2026, a retailer redesigns their site. They move the checkout button 3 pixels to the left and change the underlying HTML class.
And suddenly the environment has shifted away from the AI's training distribution. In a clean benchmark, the website never changes, but in the real world, APIs time out, users provide ambiguous instructions, and buttons move. The AI suddenly hallucinates clicking a button that just no longer exists.
So hiding variance on a single isolated task is bad enough? But AI agents aren't just answering single trivia questions anymore. They're designed to execute long sequences of actions.
Right. They act over time. They take dozens, sometimes hundreds of sequential steps to complete a single goal. This introduces the arithmetic of deployment.
The paper draws a sharp line between 2 metrics here, pass at k, and what they call pass to the power of k. Let's define those because pass at k sounds like a password requirement.
It does. So pass at k is the metric AI researchers love to use. The k stands for the number of attempts. It asks, if I give the AI 10 attempts at this task, did it succeed at least once? That's pass at 10.
Which is an incredibly optimistic metric. If it gets it right on the 9th try, the researcher checks the box and says the model is capable of the task. It just measures whether the skill exists anywhere deep inside the neural network.
But in production, you do not have the luxury of 10 tries. You need the agent to succeed on the single attempt you actually run. And when a task is long, you need it to succeed on every single step in that chain. That's pass to the power of k. Does it succeed on step 1, and step 2, and step 3?
The compounding math of reliability here is staggering. Let's ground this in a real scenario. Say I give an incredible state-of-the-art AI agent a workflow. I wanted to read my morning emails, extract the invoices, cross-reference them with my bank ledger, and draft reply emails for the missing payments.
Okay, let's call that a 50-step sequence.
Sure, and assume the agent is highly capable. It gets every individual step right 95% of the time.
A 95% success rate per step. In isolation, a 95% is an A grade. You'd think a system scoring 95% is ready to launch.
You really would.
But what is the probability that this agent actually finishes the 50-step inbox job successfully?
What is it?
The math is unforgiving. When you chain those probabilities together, you multiply 0.95 by itself 50 times, the reliability collapses. The agent's chance of actually finishing the job isn't 95%, it drops to just 7.7%.
Wait, 7.7%, let that sink in. A 95% success rate sounds like victory. But stringing those steps together turns a tiny 5% wobble into a mathematical guarantee that you will lose 9 times out of 10. If the agent misreads a date on step 42, the entire workflow fails.
The horizon itself is what kills the agent. The longer the task, the closer the probability of success approaches zero. And this explains the massive dissonance in the AI industry right now.
Executives look at benchmark scores rising from 90% to 95% and declare that AI agents are ready to replace entire departments.
Meanwhile, developers actually trying to automate daily workflows watch those exact same agents faceplant repeatedly. The capability is indeed rising, but reliability decays exponentially over long horizons.
So the math is brutal, and our leaderboards are laundering the variance. How do we fix this? The paper calls for a science of reliability. What does that actually look like in practice?
It requires a fundamental shift in how we test models. We have to stop treating average accuracy as the ultimate metric. We need to evaluate the distribution of outcomes. Instead of running a test once to get a score, you run the identical test 1,000 times and map the variance.
So you graph the wobble. You measure the floor, not just the ceiling.
Exactly. Kapoor and Narayanan also emphasize the need to evaluate the worst-case scenario. When the model fails, how bad is the failure? If you're deploying an agent to handle financial transactions, an average accuracy of 95% is irrelevant if the 5% failure mode involves sending millions of dollars to a random offshore vendor.
Right. You cannot survive the worst case outcome.
No.
And this brings up a critical distinction in the paper, studying how an agent fails.
Yeah.
Not just the frequency, but the nature of the failure. Because there's a massive difference between failing loudly and failing silently.
A loud failure is legible. The agent encounters an API it doesn't recognize, throws an error code, alerts a human, and just stops executing.
Software engineers love loud failures. You can write a recovery protocol for a loud failure. You can build a safety net.
Yeah.
So why don't AI agents just do that? If it doesn't know the answer, why doesn't it just throw an error? Why do we get silent failures where it confidently hallucinates a fake SQL query that deletes a database?
To understand that, you have to look at the underlying mechanics of large language models. At their core, LLMs are token predictors. They do not possess a concept of truth. They calculate linguistic probability based on their training data.
They're essentially highly advanced autocomplete engines.
Right. And more importantly, during their fine-tuning phase, typically reinforcement learning from human feedback, they are heavily optimized for helpfulness.
Yeah.
They're mathematically incentivized to provide an answer that looks plausible to the user.
Oh, so admitting I don't know or I cannot complete this is often penalized by their internal architecture unless they are specifically and heavily trained to refuse.
Exactly. They are structurally designed to be people-pleasers. When faced with an unknown variable, the highest probability path is often to generate a plausible-sounding sequence of tokens rather than stopping the sequence entirely.
And a people-pleaser is a terrible trait in a production environment. An unpredictable, silent failure is a landmine. You cannot build a business on a minefield.
No, you can't.
This is why studying failure, cataloging it, understanding the shape of it, is a rigorous scientific act, not just an afterthought.
Think about the previous research we've covered in our deep dives. We explored why reasoning models need external memory to avoid losing the plot. We discussed world models that allow agents to simulate actions before taking them.
And every single one of those innovations was a gear added to the machine to stretch the ceiling.
Right.
They were built to extend capability. But this paper asks the ultimate question. Once you build that incredibly capable machine, how do you prove it won't blow up in your face?
A prototype proves it can work. A product proves it won't break.
The transition the whole field is feeling right now in 2026 is the agonizing shift from hype to reliability. For the last few years, progress looked like a model jumping from 88% to 91% on a leaderboard. It was thrilling, but it was a mirage.
The truly revolutionary AI, the one that will actually change how human beings work, will not be the one that chases that final few percent on a benchmark. The revolutionary AI will be the one that might only work 2 times out of 3, but it only fails in ways you can see coming.
Because a predictable failure is something you can build around. Trust is the final frontier. We have spent endless compute cycles proving that our AI agents can cook the most spectacular dinner imaginable. Now we were all just standing in the hallway trying to figure out if we could finally leave Marco alone in the kitchen.
And until we establish a tree science of reliability, we're going to keep ordering a lot of 10-100 p.m. pizzas.
Before we sign off, here's a final thought to mull over. If we eventually do solve this, if we build a perfectly reliable agent, one that never hallucinates, never fails silently, and always mathematically knows its exact limits, does that perfect legibility make it feel more human or entirely alien? We'll leave that with you.
You've been listening to a deep dive on Bearded AI Guy. We are two AI agents, and today's research was curated by the human architect, author of AI Agents in Action.
We want to hear your perspective on this. Have you experienced this gap between an impressive demo and a frustrating real-world deployment? Drop your thoughts in the comments below, and please subscribe to the channel so you don't miss our next deep dive.